Greetings, students. If you struggle to understand factor label method, there are other ways to do mass-to-mass stoichiometry, so this video is made for you. That being said, this video is meant to correspond to Unit 7.2. However, I will be going over some information that is in 7.3 on volume conversions, because the methods used here can be used with conversions with volume. It just requires a slight tweak to how they're done. So in this video, let's not do factor label method, as that seemed to give you some trouble. Instead, let's focus on doing stoichiometry by proportion. So please ignore everything we have talked about in this unit so far, and instead let's focus solely on writing proportions. A proportion is where you set up some ratio. For example, you know that in $1 there are 20 nickels. So if I told you that I had 110 nickels and I want to know how many dollars that is, you could set up a proportion. Some number of dollars would be 110 nickels, and you would cross multiply, giving you 20x equals 110 times 1, so x would be 110 divided by 20, or $5.50. This is how a proportion works, where you have a known conversion and you solve for your unknown. Notice that in a proportion, the numerators are the same, the denominators are the same. So this will be different than factor label method, thus me telling you, ignore everything we've done so far. In a balanced chemical equation, the proportions of one reactant to another, or a reactant to a product, have to maintain the same as the balanced reaction. So in our propane example, it says 48 grams of propane are used up. How much carbon dioxide is that? This is our unknown. 48 grams of propane is some mass of carbon dioxide. We can set that equal to a known. The known amount would be from the balance equation, where one propane is 3 carbon dioxides. However, this is grams of propane and grams of oxygen, meaning our known has to be the grams of one propane to one carbon dioxide. So you would put the molar mass of one propane here. So 3 carbons and 8 hydrogens would be 44.11 grams. Here we would put the molar mass of 3 carbon dioxides, which would be 3 carbons and 6 oxygens, or 132 grams. These ratios have to be the same, so we could cross multiply and solve for our unknown grams of carbon dioxide. 48.6 times 132 equals 44.11. X divide by 44 on both sides. We'll solve for the grams of carbon dioxide, giving us 145.5 grams of carbon dioxide. Proportions work just as well, because you end up doing the same steps as your factor label method. Make sure that if you are talking about grams, that you are putting the molar masses of how many are in the balanced chemical equation when you set up your proportion. If, for example, we were talking about volume of a gas, so now talking about stuff we learned in Unit 7.3, if we want to know how many liters of carbon dioxide are produced at standard temperature and pressure, 0 degrees Celsius and 1 atmosphere, our proportion would change. We would have grams of propane in the numerator. In the denominator, we now have the liters of 3 carbon dioxides. 1 mole of any gas at standard temperature and pressure is 22.4 liters for each mole. So since we have 3 carbon dioxides, that would be 3 times 22.4, giving us 67.2 liters. And again, we could cross multiply, giving us 48.6 times 67.2 divided by 44.1 to solve for x, or to tell us how many liters of carbon dioxide we would end up with. So you would have 74.1 liters of carbon dioxide produced. Again, as long as your proportions have the same units in their numerators and denominators, and the ratios are based off of the balanced chemical equation, proportions are a way that you could do your stoichiometry.